here in dark. Well, I hope it's okay. That we don't have light here, but it's for now. It's just for the time being. Well, first of all, thank you all. I would like to start my speech with ladies and gentlemen, but I don't see any ladies here except for me. So just gentlemen, well, good to see all here. I would like to give a special, big, great thank you to our subject matter expert, for you, Dr. Randall. Thank you so much for being with us. Let us give you applause. Yeah, and then to you all. Thank you. Let me introduce my colleague Yerbolat. He will be helping out with the minutes meeting at the end. And myself, my name is Darya Musharova. I am an EOR expert working for KMG Engineering. This is a national company here in Kazakhstan. We are trying to help out our old and already water-cut oil fields. So let me give you my personal message before I start. I would like to ask you to not only listen to me, but actually try to give us your valuable opinions, your valuable experience, share with us your best practices in terms of lab testing. When we talk about polymer lab testing, this is very important for us. We are struggling with some experiments. We want to modify some experiments. We want to make it perfect at some time, somehow. So without your help, without your support, input, we won't be able to do this. So please let us start, and hopefully at the end we will have something fruitful, something very nice in terms of the end result. So my presentation will be focused on just one question. And this question is what and how needs to be measured when we talk about polymers. And this is just one graph presenting the effect of oxygen and iron on polymer solution stability. And we know when we have these two factors, both oxygen and iron in the solution, it destroys our polymer solution very much. But let's start from the beginning. So, talking about successful implementation of any EOR project or any EOR technology, there are a few parts that we need to perform very well to make our best, to do our best to get a good result. And when these few pieces will be put together, we'll have a great picture. So the first puzzle of this process is selection of the method itself. What do we do to select the right method for our oil field? We go to screening. There are screening criteria, very different, very various nowadays, and we compare field parameters with these criteria and see if it matches. If it matches, it's a good start, let's say. It's not the solid answer yes to this technology, but it's a very good start to start going deeper and deeper to analyze if this technology fits your oil field. The second part is the pilot area selection. Our oil field is great, it's huge, and we've got different geological characteristics, and we've got some different infrastructure, surface facilities also can be different depending on the area of your field. So we do the pilot area selection, and we try to get the best pilot area, and we want to fix it and keep it from other geological let's say other geological activities. So the next one, once we have a reasonable technology here that we've selected by screening, and and once we select the best pilot area, what do we do next? We start to select the right chemicals, and this is a very important part as well, since we've got to analyze our cores, analyze our oil, our water, and try to see which chemical works for these conditions. We don't need to forget about the temperature and the pressure of your reservoir, as well as other details which may take place as well. So I would like to make a comment here on this chemical selection process as well. Just now, a few minutes ago, we've heard the presentation from one of the experts. He was talking about surfactant selection. He was the last one before the break, and he mentioned the following. He said that it's very important to understand the chemistry of the surfactant. I was thinking at that moment that we don't understand the chemistry of the polymer that much, and we don't understand the chemistry of the surfactant that much in our company. We work with already ready solutions. We call the company and say, hey, I need a polymer. My temperature is 90 degrees and my salinity is 200. Can you give me the right one? Of course, we will also give him details, but we are asking for the ready product, already, accomplished. And the same we do with the surfactant. We just call and say, okay, we want to order this surfactant if it fits our oil field. We don't understand the chemistry behind. So that's, the reality is bad or good, maybe not good, maybe not bad, but it is the way it is. So this, I'd like to mention this, just for you to know that we don't understand the chemistry that much of the polymer. We just work with the given to us polymers from the companies. The next one is simulation. This part, sometimes we don't have it in our process. We don't have, maybe we don't reach that level of modeling, the desired level of modeling yet. So we don't really trust our simulation that much. Sometimes we have it, sometimes we don't. But we don't rely on it. We don't rely on the results. We do rely on the lab testing and just our calculations. And we use analytical methods to make additional recovery calculations. We don't rely on the simulation in our company. And the very last composition of this whole process is profitability. This is where we count the money and see if the project is economically feasible or it's not. So this gives us an answer, yes or no, at the very end. So if we do all these parts in our best way, with our best efforts and really good results, basically we do high quality realization of each stage. This is what we get. So the next one. Our polymer testing can be, if we look at the polymer testing, we can make a few big groups of laboratory tests. And let us look at them now. So the first one is viscosifying power of polymers. Basically, these are rheological tests when we take the polymer, mix the solution, and then measure viscosity. And we do different measurements. We can see viscosity of polymer solution depending on its concentration, depending on the salinity, depending on the temperature, depending on the shear rates, and then so on and so forth. So these all tests, they live in this group. The next group is devoted to polymer solution losses. Which degradation types can we have? It can be mechanical degradation, it can be thermal degradation, it can be degradation, chemical degradation as well, degradation due to some other factors such as having, if you have free radicals, if you have oxygen in the system, if you have let's say if your pH level changes, it also can lead to change in the viscosity of polymer solution. So these all losses we analyze and test in this group. The next group, the third one, is where we measure mechanical degradation of the polymer solution, and here we use real cores, water saturated cores, to see how much of the polymer solution we lose here. And the last but not the least for sure, this group is related to pore flooding tests. These are most important for sure. We need to get the real cores and inject our polymer solution and see different parameters such as sweep efficiency, recovery factors, absorption, what else? Resistance factors and others. So if we do all these tests in a proper way, in a correct way, we get the right polymer. We believe we get the right polymer for our oil field. I would like to have a live discussion with you. It's not about me, it's about us and our work. And let me excuse me if I will just ask some questions during my speech, and I'll ask you about some of the things. So let us go further. And as I told you, we call the company producer producing polymer and say, hey, I need a polymer, help me out, and he'll send it to us. But for the company to get the right polymer for us, they need a few parameters. So we give the company permeability and porosity and pore size data for them to be able to screen the right polymer for us. We, for sure, we give them water sources information. First of all, we analyze which sources we have. If we have highly saline water and low saline water, for sure, we will try to work with the low saline water, and then we give information to the company for them to help to screen the best polymer for us. And then for sure we give this information as well, which is reservoir temperature and current state of development. Well, almost all our fields now at the very last stage of development, which is the high water cuts and low oil rates. So basically at the very end, and water cuts are more than 95%. So even more than 98 or 97%. So it's almost there, but it's not there yet. And then we start doing the polymer selection. What do we look at when we get the polymer? Well, first of all, it's like when the person is born, the child is being born. What do? We measure his weight, and we measure his height, and we measure some other, and we determine his sex, or female or male. We do all these things. The same with the polymer. So once we get the polymer, we measure what active component content, hydrolysis degree, molecular weight, viscosity, and some other parameters I'll show you later. So this is the first step. We do this determination. And then once we know what polymer is, and the question for y'all, why do we do this? Or what do you think? Why do we need all these parameters? Why?
To study
What for?
to understand the viscosity ability of the polymer solution that you want to use.
Yes, but what else? It's not the main reason. What else?
So you want to make sure that your polymer is compatible with the reservoir condition.
Yeah, but
And while making sure, you also want to make sure that you do achieve that viscosity with a minimal concentration. So you need to consider molecular weight as a
Yeah.
variable as well.
yeah, but why? Like the most important reason. For sure, you're right. You're right, absolutely. But there is another reason, which is also important. Why do we need all these parameters? Talk about the strategy, the future, maybe little like close future of the project. Why do we need all these parameters of the polymer? Or what? Any ideas? Brainstorming? Hey guys.
What kind of ability which how to
Not
substitute
quite.
calculate?
Closely, but not there yet.
To build like a data bank? Or
It's warmer. It gets warmer. Yeah, yeah, but not there yet. Okay.
identifying polymers for incoming reservoirs, like
Yeah.
delineation of your selection of polymer.
Yeah, closely, very close. Well, we do this all for our pilot tests and field application. Why do we need all these parameters? So once you get them, when you start your pilot, and once you have your huge amount of polymer for the pilot, we want to make sure that the pilot polymer quality is the same as the lab. Yeah, it's the quality check. It's the same as the one we get during the lab test. If they're the same, we're okay. But from our experience, I can tell you that we've got big problems with this comparison. They don't match. And we gotta stop the project, and we gotta lose a few years to start the project just because the quality is not the same. So for us, it's very important to fix the parameters at the very end, at the very beginning, for them to use and to compare with the later quality of the polymers.
Sure. As I represent SNF, a polymer manufacturer, I can give a small part of an explanation about why you have some lack of matching industrial products and a sample you could receive during your evaluation. Is it when you receive a polymer? This is not like when you go to IKEA buying a table or a chair. It will be always the same product everywhere in the world. For the polymer manufacturing process, we define for a given range of different parameters a specification which include within this specification we define that the polymer is belonging to as a certain name, and if we have other properties we have another name of the product. So let's say if a polymer A will be a boy and have 170 to 180 meter high, 70 to 80 kilogram. So if I send you a boy, 175 centimeter and 75 kilogram, you say, oh, this is my boy, I want this one. But I will be from the manufacturing process unable to deliver you the same exact boy polymer every time. So you will have some. I understand your disappointments because you ordered these properties, exact properties, but it is not as straightforward process to have same exact property. You have to account some specification range, some relax in the expectation, and the most importantly for me is defining molecular weight. It's helping to have some basic, very basic selection for which molecular weight address for which permeability. We all know that in the room, no doubt about this. But I will not struggle knowing the very exact molecular weight, because you will sooner or later hit the wall of the accuracy of analytical techniques. So in this case, the more I know nothing.
Thank you.
And I will probably more focus on what are the rheological properties of the polymer, which actually are the combination of all the properties, the physical, chemical property of the polymer, the anonicity, the molecular weight, the chemistry, the hardness, the salinity, tolerance, chemistry based to the brine. All of these properties that you are more or less spending a lot of time, a lot of money in the lab to characterize. This is your first phase. All of these properties combine together and result in viscosity. When you measure viscosity in the lab, it is more or less like you measure molecular weights. So why? I don't mean you should measure molecular weight, but this is all of resulting of in this. And then you can rank polymers for a given specific consumption, for a given viscosity target. You can rank your polymers according to this, and it will be very simple process.
Thank you. Thank you very much. Yes.
I totally agree with you, because the process of manufacturing the polymer in the polymerization, it's almost like a random one. So you can get range of molecular weights. What is important is if you want to make a quality check, is to get the patch, from or each polymer patch. It should be having the similar property. Yeah, but for molecular weights, I don't think you can get the same molecular weight average. So.
Yeah, thank you very much. Yes, for sure we do account for this range, existing range. We understand that it's not like the exact number. We do have a decline, a small decline towards a bigger and a lower value of the target value. So we do have this range, and we do understand that it's not. It can be not like the same one. But the cases I mentioned, when we didn't have like this match at all, it was like black and white. When it gets soluble in the lab, and when it does not get soluble in the field, so it's that different. It's not, it's something that for sure gives us an understanding that the polymer is different, totally different. So thank you very much for your comments. I really appreciate it. Yes, and I do agree with you all. Thank you. So then we do rheological studies. I mentioned already. We build different curves, different dependencies on the polymer concentration, on polymer, how polymer viscosifying power depends on the temperature, and so on and so forth. Once we do those, the next one is resistance to degradation. Here we look at the mechanical degradation and try to see if it's big or not. We do want to have a more stable polymer solution rather than it will be just destroyed in a few inches of propagation in the formation. So that's also important for us. And then we do core flow tests. If at some point we do have bad quality polymer, identification. For example, at this point, if we see that polymer is not soluble, we refuse and give up on this polymer and say we don't want this polymer anymore, and this polymer does not don't proceed with this polymer anymore. So we exclude it here. The same here. If our polymer solution is not mechanically stable, we say goodbye to him and leave it out. And we leave in the project only these polymers which are stable and of good performance. Sure, please.
So you need to have a balance between viscosity power and resistance to mechanical degradation. If you want to generate a very high viscosity, you need to go for high molecular weight polymer, right? But that high molecular weight polymer is prone to mechanical degradation than the low molecular weight polymer. So you need to have a balance. If you want to minimize the degradation, then you have to go for low molecular weight polymer and increase the concentration, which is relatively less resistance to mechanical degradation.
Yeah.
So there's an optimality that should be considered if you want to have a balance between viscosity and mechanical degradation.
Thank you.
And as Dr. Randy demonstrated in from the field project with Dr. Marat, degradation may not be an issue in the field if
Due to fractures. Yeah.
Perforation also, if you have a different, in the injector, if you have the information of having density of perforation, providing you available surface of injection, you have apparent shear rate of degradation much lower than what you would imagine
In the lab.
in the lab.
Yeah.
So this can be also information gathered from the
field,
project,
yeah.
or this can be also re-perforated before the
Yeah.
execution.
Thank you very much. Yeah. Thank you.
How do you determine the solubility of the polymer in the water? With which test you are using?
A simple test when we dissolve the polymer and mix it with water and then see for how long it takes to reach the stable viscosity. And if it gets stable and there are no fish eyes or some unsoluble particles, that's okay. There is a special procedure.
So you are measuring the viscosity as the developing viscosity.
Yeah.
So this is the hydration test.
Yeah.
I guess.
Yeah.
Michelle has an interesting situation. I mean, he has extremely high salinity, and like a lot of us, we work maybe with really low salinities, right? And it's no big deal to get the polymer into solution. Like melting point is the solution water is only 2,000 to 3,000 parts per million TDS, but his is crazy high. And so that really is an unanswered question in my mind. I know yours in Kazakhstan too. You have pretty darn high salinity, probably not as high as his.
What's yours?
260 ppm, 1,000 ppm.
I understand. We don't go that much. For us, it's about 120 for now.
So I mean, the question is, we know that when we put polymer in water and we look at it visually, if it's distilled water or really low salinity water, it's really clear, right?
Yeah.
And you think, I feel good about that.
Yeah.
But the more saline we make it, especially when we get above 5% total dissolved solids, it gets hazier and hazier. And a super good question, which I know you have to face, and maybe Ludwig has some insight, is, obviously when you start seeing cloudiness, there's some kind of molecular association. And whenever you see a molecular association, the question is that going to really propagate? Is my porous media going to filter that out? So maybe you have some insights on what to do there.
The haziness you refer is the association, the kind of cloud point of the polymer with the divalence and the
So he's got a high
creates
divalent cation
molecules.
content too. What's your divalent cation content?
21.
Yeah, so 260,000 parts per million like salt, sodium chloride, and then 1/20 of that, that's still a darn high salt and calcium content, right?
It's it's a lot, and if you use a regular HPAN, dissolution will be impossible, or you will have cloudiness. So, but if you use, tolerance,
Modified.
hardness,
Yes,
hardness,
But he's
tolerance,
getting it
monomers
into
like
solution, right?
ATPase.
Solvated one is.
Yeah, he's getting it into solution, which I didn't think was possible.
You may be able to solvate the polymer, but when you speak about you mentioned that the solubilization is accounting the viscosity stabilization, and also you look at the fisheyes or insolubles. For me, fisheyes or insolubles are different. In the wording we have in the company, and we try also to spread out. The fisheyes will be more. You miss something during the dissolution. Dissolution is really properly hydrate each individual grains of polymer in the water so that they don't stick together and create a fisheye. So a fisheye will be hardly be dissolved. You need a long time. But this is due to improper dissolution methodology, but this is not. This can be corrected very easily. Or this is poor, but this can be translated in the field. Because I always like to go to do some switch from lab.
Yeah.
The field lab is not the real life. Field is more appropriate where you have the challenges of the implementation of what we are creating in the lab, and how you can implement it in the field. So this can translate it in a poor quality equipment with, in the past when I started in the industry, we had much more having eductors type of equipment. This can work, but for longer time dissolution, but also if you have some water interruption or some pulse, you have some clots, some fisheyes. But the other you mentioned the insolubles. And insolubles, it's also part of the manufacturing process of the polymer. It's, I would say, nearly unavoidable to have non-insoluble polymer. This you can translate with filtration. If you observe that once you have a stable viscosity, this sample can be transferred to a filtration test and see if it is appropriate numbers, 1.2, 1.5, depends on the criteria you put. But if your filter ratio is way too high, of course your polymer is bad quality, full of insolubles. It is not even, I would say, EOR grade.
From your viewpoint, what are the insolubles? Are they just super high molecular polymer? Are they solid?
They are like what we like to have polymer are made of random chain polymerization.
So it's organic.
And sometimes you may have some kind of gels, like cross-linked molecules together.
So it's just polymer that's...
It is polymer
Okay.
that it's like an hydrogel.
Yeah.
This, if it is soft hydrogel, you will not even notice in the injection. They will propagate, or even they will be destructed through the pressure.
What's the highest salinity of water that you've made polymer up in the field?
260 or 250,000
Really?
gram per liter.
Is that his case, or is that somebody else's?
In Anak or Assad, Bab and Assad project.
Where is it?
In the Middle East.
Oh, so that maybe it's your reservoir.
UAE. In UAE.
Oh, okay. And no
120 degrees. No.
So like normal polyacrylamide or
Not
ATBS?
normal. ATBS based.
I guess.
ATBS based.
SAB.
SAB. Yeah.
And no problem.
No.
Okay. Oh,
In the lab, we found it stable for multiple years, 5, 6, 7 years.
Nice.
What is the salinity?
And
Average
injected
salinity?
in,
For us,
in the reservoir
120 right now.
very,
120.
very
Yeah.
successfully.
We do have more salinity, more saline reservoirs.
Yeah, yeah.
But we don't inject polymer there.
You raised a good point about the filter ratio. It's like being around 1.2, 1.2. The second important thing is the absolute filter time. You know,
Yeah.
because the measurement of filter ratio, it's okay, but how long it take for this solution to be filtered? So this is one of the things that I don't see it in the literature. They don't report it. So besides the filter ratio, I think we should also concentrate on the absolute filter time. If it's taken so long, then there is a challenge in the objectivity.
Yeah, but also there is, I mean, you know, although as I said, the more scratch, the more, I mean, there is more unique, there is something to scratch in the evaluation methodology. We are conducting some literature survey, and also we have some experimental done currently about the impact on the filter type.
Yeah.
On the oncoming result. Depending on which filter you use, you can have a product, a qualified product or a non-qualified product. So outcome is disturbing results.
There are
It's
usually two types of filters.
Yeah, I mean from same pore size, but depending on the materials of the filter, you can have a good or bad product. So it is really this, the way of testing is the root cause of much misunderstanding or project closure directly at the lab scale. Because of, I don't mean improper laboratory evaluation, but non-aligned understanding in the evaluation.
What's your preferred filter?
I mean, it's we have it's too early to say for me.
So cellulose, nitrocellulose, nucleopore, doesn't matter?
It matters. I mean, for as soon as you go for very low pore size, like 1.2 micron, which is the type of filters used for the low permeability reservoirs, which is not the case in Kazakhstan. These are changing, and the choice of even the diameter, filter diameter, is important. But when we use 3 or 5 micron type of filter, 47 millimeter, nucleopore is perfect. It's perfect.
Thank you for valuable input. Very nice. All these comments, it's like a new book for us to write. So please listen to all these discussions which are going on meanwhile. These are very important ones, even more important than my presentation. So yeah, thank you. So yeah, if something is bad in the meantime here, we just get rid of the bad products, polymer products, and leave ourselves with the good ones. Actually, my colleague Yerbolat, he is the one who is doing all these lab tests. So he and his group, he's done a lot of polymer selection projects. He's done a lot of lab work. So if you have like specific details on or want to discuss with him some specific things, please welcome. He'll help. He'll explain. So let us briefly go. I'll go kind of faster somewhere and something I already said. I don't want to, go over this again. So let us go over the laboratory studies on the selection. I want to ask you, beg you, if you want, on your feedback, what would you advise us to improve? What would you advise us to take a look at, review maybe, revise maybe, because we want to improve our polymer selection projects, right? Yerbolat? Yeah. So a lot of words, but I'll just go briefly on these names of the tests that we do. So first of all, we want to analyze the core. We do the standard core analysis test. I don't want to go, these are the laboratory procedures, which are very common in the world, nothing new. So we do the standard core analysis to understand what's the permeability, what's the porosity, what are the pore sizes, distribution. Sometimes we want to see how much shale we have. Sometimes we want to see, not sometimes, we do analyze the mineralogy, what's inside, lithology, and all these things we do here. So then we study the reservoir fluids. For sure we do the chemical composition of the water test. We do we measure some physical parameters of the waters. We do the special analysis on how much iron we have present. It's both iron 2+, iron 3+ content. If we have oil and water emulsion, we also measure that. Also, if we have, let's say, if we have some solids present in the water, we want to know the nature of the solids, how much solids we have in the water. So basically, also traditional tests, I would say here. And then we choose the optimal water source if we do have this choice. Sometimes we don't have this choice. And my boss asks me sometimes, Darya, is it worth thinking about desalinization processes for our waters? And I say to him, probably not, since it's very costly. It's better for us, it's my opinion, it's better for us to just order and buy just a little more expensive polymer rather than, do the revision of the whole water salinity, water preparation or water treatment. It's more costly rather than buying a polymer that fits our conditions. Then we do the rheological tests. Here we do the preparation and we use the standard APR RP63. I'm sure you all know these procedures. And we do the dissolution time measurements. We determine we do determination of concentration according to the target viscosity. So if we know our target viscosity of the polymer, we will see how much powder is needed for each polymer to achieve this target viscosity. And for example, one polymer solution can be of 1000 ppm, that gives you this target viscosity. The other solution gives you a number of, let's say, 2000 ppm. And then you compare and see, well, the second one seems like less attractive and more costly.
Excuse me.
Yeah.
So, which shear rate you would use to compare?
Which one?
Which shear rate?
Shear rate. Oh yeah, it's also it's traditional one is 732. Yeah.
But we
exactly.
feel like it's mostly that polymer solution is gonna be Newtonian region and it's going to propagate to the porous media.
Yeah. Well, it's not just one number. We do this curve with different shear rates.
Full complete.
Sure. Yeah. Sure. Yeah. Starting from 0.6 or even less, and going to up to sometimes 200 or 300 1 per second. So yeah, that's the whole region. And then sorry, I'm here, right? Okay, then we do check for sure. We check the compatibility of polymers with different waters, and we do the long-term sensitivity for Almaty. Well, our problem is that we are always short on time, and this is, that's our reality. Is Yerbolat for sure it's like this. Okay, you can justify. Well, and since we're always short on time, we don't have this time for doing this stability test in its best way. So our stability limits, let's say, only at 30 days or 45 days. We don't go longer. We can't. We don't have this time. So long term for us, it's 1 month. Yeah.
This stability actually is dependent on your type design, isn't it?
No. Why would it be?
Because if you have closer, injector production, then you need like short time.
Residential time.
Yeah.
Well, but we want to see once we inject the polymer solution and it stays in the underground, we want to make sure it does its work.
It's injected and produced, isn't it?
No. Why would it be produced? We don't want it to be. We don't want to produce the polymer that we inject. We don't want.
You produce it, I guess.
We do, but it's very small amount. Most of the polymer stays in the formation.
Amplifying on Michelle's point, a key question we always want to ask in the lab is, how is what we're doing here relevant to what's in the field?
Yeah.
So he says sometimes we have very short well spacing, sometimes we have very long well spacing. If we have very long well spacing, it can take a long time, and we still need the polymer to be stable for a longer period of time. And if it's a short well spacing, maybe we don't have to worry about it that long. Madar had a really good point too, is a lot of times we use 7.3 reciprocal seconds as a standard for our shear rate. And at Milne Point, we started with that because the field guys are saying, I don't want to spend too much money on polymer. I want to get the right concentration of polymer for what I'm doing. Because that's all about money there, right? So we started, we said, okay, 7.3 reciprocal seconds. Well, at 7.3 reciprocal seconds, the viscosity of the polymer is maybe not that high. And we asked the question, what is my real velocity in my reservoir? Now at Milne Point, we have horizontal wells, so our flow rate is substantially less than 7.3 reciprocal seconds. It's more like 1 reciprocal second, maybe lower than that. So what we could do, what it immediately said was, we started with a design of like 1,750 parts per million polymer, and when we realized, no, we get that much viscosity at 1 reciprocal second by only 1,200 parts per million polymer, that's a big saving, right? So just that simple little piece of information made a big difference to us, in just knowing what there is in the field.
Thank you. Yeah. Okay.
And regarding the thermal stability, which water do you use to conduct
This test?
the test?
Yeah,
this test?
injected water for sure.
Injected water. So the one sample from the field, or you
We
create
don't.
synthetic?
Yeah. Sometimes both. Sometimes either or. Depends.
Okay.
We can do both. Yeah.
Okay. So for
Which one would you suggest?
I would suggest, the easiest way is to, and the most
Representative.
not representative, but the one you can reproduce the easiest way, and you can have a fair comparison,
Model.
is to use a synthetic water composition. However, this will not you will have still to have bear in mind all the contaminants you have in your water, but this has to be addressed on the water treatment aspects of the project, and also in the equipment implementation of the project. Because we all know that oxygen, polymer, and ferrous iron, or H2S, they are not a good mix together, especially for the polymer, which will be reduced drastically. So this has to be, if you want to evaluate this in the laboratory, you will have to deploy very sophisticated tests, and even that you will not be able to have representative and reproducible evaluation. However, this ferrous oxygen content has to be addressed really when you have, it can be addressed in troubleshooting mode when you are already injecting and you don't match the viscosity you have. So you enter in troubleshooting mode to have the root cause of your lacking viscosity.
So that's an excellent point, and I want to elaborate on that. So the key thing we have to worry about in a stability test is exactly that interaction. Oxygen, iron, H2S, anything else that might be there. If we do a lab test that doesn't address that, we have to make sure we're interpreting our lab test correctly, right? So I mean, for me, you're absolutely right. Doing these sophisticated long-term tests with no oxygen and maybe the presence of iron or something else in there take a lot of effort. So a couple of points. Go ahead if you have something.
No, please, let you finish.
Okay. So what I'd say, if we're only doing a short test, 45 days, how does that 45 days compare to our real transit time in the reservoir? If it's not anywhere close to what the real transit time is, maybe we're addressing a different issue. And one of the things that most of us don't, as operators, we don't know, is we know that different vendors, different polymer suppliers, sometimes put different additives, proprietary additives in their polymer. Maybe to help dissolution, maybe something else. But we don't know what they are, and we don't know the effect on our stability, right? So if I do a 45-day test and the polymer falls apart, I don't suspect the polymer. I know basic polyacrylamide has a certain chemistry. I mean, yours and Chimera's and somebody else's basic backbone is all the same. The reason it's going to fall apart differently is maybe some other additive that's in there. And so, you know, when I do a 45-day type of test, something like that, maybe that's the thing I'm looking for. And I have no idea why it's falling apart with a bad polymer, and you guys maybe do. So any insights on that?
Yeah, we spend a lot of time evaluating the additives on the thermal stability of the polymer. It was well before the apparition of what we call now the aspirin for polymers, ATDS. We spend a lot of time and effort to try to have high polymer, regular polymer sustaining high temperature cases, and actually we didn't succeed. We switch from having additives to just playing on the polymer chemistry, having ATDS based polymer when it's required, when you have your polymer, your water composition or temperature require such tolerance to the harsh condition.
Which is better for us because then we know a little better what we're dealing with.
Yes, and I mean, it's also way better for a manufacturing process, because just simply you have to blend both powder to powder to make sure they are uniformly mixed together. So it's really much more simple for everybody.
Yeah, we like that.
And
I like
it's
that.
It's straightforward, and the evaluation way of especially the thermal stability is really key to have representative results for the ATB.
Alicia?
Also, it has an added advantage that ATBS addition, as Dr. Randy demonstrated in his paper, that it minimizes the retention when compared to HPAM. Even if you don't have high salinity, high temperature,
It can be variable.
if you use ATBS in the place of HPAM,
This can be
and maybe the retention would be minimized, the tiling would be minimized, as we have demonstrated with the new recent paper 2020.
Hello everyone, I'm a representative of service company, so we are deeply involved in this topic. And my question is, when institute is doing lab tests for research the optimal polymer on the water, synthetic or real from the site, and till the start of injection, it takes sometimes like half year or maybe 1 year. So in the end, when we are coming on site, the water is totally different. Should the tests should be repeat, or what should do? Maybe some plus minus, I don't know, 15% on all the results we should think about or not. What is, do you understand?
Yeah, so my personal view is, you know, before ATBS, all of our polymers were polyacrylamide, right? I mean, they were just the same backbone, and you have to ask the question, why wouldn't they have all the same stability if I did everything right, right? So we have a lot of people in the laboratory over the past 50 years who've done some excellent studies and said this is what the basic stability of that polymer should look like. So that means maybe we don't all have to do the same tests over and over again. We rely on, okay, this is the basic material that we have, and if it does something different from that, then we start asking why. But at least it says, you know, the polyacrylamide ought to be able to do okay, so long as something strange is not happening, like some strange additive is put in there. Now we put in ATBS, and we know the mechanism of the polyacrylamide degradation, largely not the backbone, but the side groups with they hydrolyze and precipitate, and we use ATBS or maybe something else to minimize that. And we know now that that helps too, a lot, right? And we have, you know, extensive laboratory studies that have kind of already characterized that. So one of my messages, let's use what's already out there, and that helps us as a guide. Yeah.
So keep focus only on viscosity.
Well, I mean, you do have to be aware of it. So maybe Darya's 45-day test is of value because you don't know if the service company has put some strange additive in it or not. But it always comes down to, is what you're doing in the laboratory really representative of what's happening in the field, right?
There is always a difference.
Well, I mean, you need to get as close as you can. Like Ludwig is saying, in the field, if we do it correctly, we won't have very much oxygen, hopefully no oxygen. And once it gets into the reservoir, there will be no oxygen, right? And that helps us a lot. So, you know, that's...
But not only oxygen. in fact,
probably what Alicia is mentioning is the base, the input data, for example, is temperature, permeability, and water quality. And the water is, we all know that polymer viscosity is related to the salinity. This is, we all agree about that. And from the initial, when the case is built up, some information are gathered. For example, the water composition, which is fine for me, fine for everybody. And we can define that as a synthetic recipe, synthetic brine composition. And when you work with it and you develop your specific consumption, rheological curve, loading curves, I mean everything, any characterization. And when you go to the field, you go back after 6 months, 1 year, 1 year and a half, but you already injecting the product, but you realize that the water has changed since
Okay, the
1 year.
salinity has changed, maybe.
Salinity have changed, and then the KPIs, which remains the same as before,
Right.
cannot be applied
Yeah, you
now
have to
because
change that.
the input data, the input water is not the same. So the behavior, let's say, yeah, the viscosity resulting for this polymer in this new water composition, which is the water composition is close but can be vary. I have an example where divalent contents change a little bit, but divalent impact a lot polymer viscosity. We all know that, and the target cannot be matched anymore. So the customer may, the end user may raise a complaint, but it's also a matter of input condition change, different from the one when we built the case. So it is always good also to have some monitoring of the water quality in terms of, we say, connectivity, or really, not spot analysis, but really continuous monitoring. This is key to help future troubleshooting.
For sure. Yes, thank you.
Good idea,
Thank you.
good point.
Plus season, temperature, outside temperature is also,
Yes,
we are
yeah.
getting effect from that. So in dynamic, we should, together with the institute, always take into account all the parameters and can accept the difference between initial viscosity in lab and on the pilot, right? In pilot area.
Yeah, that's a good point too, is if I'm getting this in the lab, why am I not getting it in the field? That's an excellent question to ask, right?
Okay, thank you. Yeah, thank you. Yeah, they say that actually water itself is a tracer. So something to keep in mind for y'all. Water composition check gives you another identification of if something has been changed in your system. So the next test is about filtration studies. Here I talked about this already. So we did a mechanical degradation test in porous medium. We try to determine the retention and absorption. Well, we don't divide these two terms, although they are different. We just call it absorption. And then we do these, sometimes, not always, we define the inaccessible pore volume, not always though. And this parameter would help if you have simulation, because there is an input value for this inaccessible pore volume over there. So also we try to understand what are the resistant factors and what is the residual resistant factor. We don't achieve this value to be 1. We always have it bigger than 1, 2, 4, and I'm glad to see this value. My belief is that polymer absorbs into the rock and it builds some resistance this way, yeah. And then whenever we inject water at the stage of post-water flush, the water will not go the same way as before the polymer was injected. So I expect to be RRF being bigger than 1, but I also believe that if we inject water for all, like hundreds and hundreds pore volumes of water for a long time, we can get this desorption process of the polymer, and we can get RRF being 1 at some point in the future, but after lots of water injected.
I have a different view. on
Please,
that.
let us talk about it. Yeah, this is the key.
Okay.
Yeah.
I think
Yeah.
largely, okay, unless you're talking about carbonates, low permeability, if you're talking about anything above 200 millidarcies, I personally think you're wasting your time with measuring inaccessible pore volume, and you're wasting your time in measuring residual resistance factor. Okay, so let me make your point on residual resistance factor.
Please.
Okay, so you made the point in reality, in a real reservoir, we're not injecting hundreds of pore volumes, we're just injecting a few. But the truth is, as soon as we start injecting water, we're getting terrible, terrible viscous fingering, right? So, you know, we're not sweeping all that polymer solution that's out there. We're sweeping a very, very narrow finger. And you think, well, I'm not injecting 100 pore volumes. You are injecting 100 pore volumes because you've got that very small finger and you're very rapidly pushing all the polymer out of it. And we know that the resistance factor that you get, I think somebody showed that, one of you two had showed that as resistance factor, maybe Hugo had shown that it takes a long time for you to approach a steady state condition. And the question is, you know, what residual resistance factor do you choose for your simulation? Your simulation believes any stupid thing you tell them, right? So they put in there, and then and if you give them a high residual resistance factor, they will say, well, that's great because I don't have to inject as much polymer. I don't have to inject a bigger polymer bank, and I could inject a smaller concentration. But if you're misleading yourself, if that's not really what's happening in the field, and I truly believe it's not happening in the field, that any residual resistance factor that you measure that's greater than 2, you do not want to believe. That's my viewpoint. Okay. The second viewpoint is you give them an inaccessible pore volume. You probably know inaccessible pore volume with the API 353-63 method is a difficult thing to do if you want to do it right. It takes a lot of time. What's the simulator going to do with that information? The truth is they say, I don't believe you lab guys, I'm going to just use it as an adjustable parameter. That's exactly what the simulators do. They ignore whatever residual resistance factor that you give them, and they just make it something up to put in there. And what they should do is, if it's a greater than 200 millidarcy rock, is just assume inaccessible pore volume is 0, because these polymer molecules are far, far smaller than any pore volume or pore throat that you would have if your permeability is greater than 200 millidarcy. So there's no physical reason why you should have an inaccessible pore volume. Okay, your simulator wants to use it as an adjustable parameter. That's great, that makes them happy because they can do all kinds of stupid things with machine learning and get whatever answer they want. But it's nonsense. Don't call it an inaccessible pore volume. Call it a simulation fudge factor or something. Yeah. Anyway, the point is, we're going to a lot of effort in the laboratory to get this. I mean, you had to do a lot of work, and it's frustrating, right? And you want to spend your time efficiently. And if they're not going to do anything useful with the information, why bother?
Yeah. Agree.
Okay. That's my thought.
Yeah, agree. Okay, thank you, Dr. Randy. Thank you so much. Okay.
Go ahead, look back here. She's got a comment.
Alice, please. Sure.
I have one more question regarding the core tests. So if you are doing some polymer choosing tests in lab, are you using one piece of core, or like model but few pieces for different polymers, or you're using one and all polymers you are flashing through this one?
Yeah, your question can be answered in 2 ways. Well, this I will tell you how we do it, but this is not the right way we do it. There is a right way of doing it. So, your question can be replied in these 2 ways. How we do it? We take this 4 or 5 centimeters rock, like this one, half of the span, even less than this half of the span. So. And this is not the right way. It's not representative. It doesn't. We do have end effects, which also disturbs the correct identification of some processes. The correct way of doing it is to elongate your cores. If you have cores that were drilled and have the length of only 4 or 5 centimeters, let us do the combined model of rocks. Do it put it stock by stock. 2-3 pieces of cores gives us a longer model, which is, let's say, from 10 to 15 centimeters, and it's much better. It's more correct. Even there is another way which I have seen in China, and I give a big applause, in my mind when I remember this case, when they do 30 centimeters of even 1 meter long core, and then measure the propagation and filtration, all these parameters of the polymer solution, and it gives a great picture of how polymer works.
More close to the
Yeah,
reality.
even there is a way of doing these core flat tests when we have a slice, when we have layered cores. We have representation of this different permeabilities, low one, high one, medium one, and then you have your pressure transient points in the middle, not only on the sides of this model. So you got a great picture of where it goes, what is the cross flow, and other questions and other matters. So yeah, we don't do it correct.
Different polymers through one sample, or for each polymer you are using each new sample, but close to
If
the
you
reality.
can clean your core from the polymer, you can use it again.
Are you cleaning it? Means not you institute.
We are not able to clean out from the polymer, and we are using different core samples.
My question then is, if you are using different core, it is different from the inside. It's close, but it's different. So how can we compare results from different cores and making some decisions in choosing of polymer? Maybe it's stupid question. I'm sorry. I'm not specialist, I'm
The
just
question
wondering.
is not stupid. No,
Thank you.
there are no stupid questions. Yes, thank you. Our cores are very similar, and it can be comparable. It can be comparable because our sweep efficiency values are not used for calculating something great. We just want to know if there is sweep efficiency at all. That is, do we have this additional recovery effect or not? So it's more not quantitative, but it's more qualitative in terms of how much oil we get from the core. And again, these cores are similar, so there is no problem.
Just
Go
a
ahead.
quick question, did you say that you can't get polymer out of the core?
No, I haven't said that.
You didn't say that?
No.
Okay, I misheard.
No. It would be a great problem. We don't face it. We don't want it.
So I think your question is a really good one from a couple of different viewpoints too. And I would say, in addition to what Darya said, I really like the linear cores, making it as long as you can, but with at least one addition, and that is to have an internal pressure tap, at least one internal pressure tap. And the reason is one of the things you're measuring when you do this is what we call resistance factor, is the apparent viscosity. And the question is, how does that resistance factor compare to our viscosity? Okay, two cases. One, they're pretty similar. Maybe the one in the core is maybe as much as twice as what the viscosity is. If I see that, I say, okay, I can believe it. If I see it's 5 times, 10 times, I say something's wrong. Maybe I'm plugging my face, right? So that's why I want the internal tap. Okay, so that's a valuable thing. Another really valuable thing, and both Jeff and I think several people kind of suggested this, is we do have to make sure that the polymer propagates, that will move. And usually that's a problem if our core is too low in permeability relative to our molecular weight, or especially if we're using something called like a hydrophobic associative polymer. Those have a lot of problems with propagation. But if we have pretty high permeability, usually we can get the polymer to move, propagate evenly. Maybe get the same resistance factor in the first section as the second section as the third section. So that's good.
Yes.
There's one thing I want to make sure we don't forget, because you did talk about oil recovery type of methods. If you say, I'm just going to fill my core with oil and I'm going to inject polymer and I'm going to say, well, how good a sweep efficiency did I get? One of the problems we have is, how do I scale that to what we're really doing in the field? And that can be a difficult thing. But there's something really important we can get from that, which is crucial, which is the relative permeability curve. Now, when you think about it, one of the really important things we want in a polymer flood is say, what concentration, what viscosity of polymer should I be in? Put in, because the more I have to put in, the more expensive it is for me, right? So if my, let's just say, endpoint relative permeability to water is very high, I have to put in a lot more polymer. If it's very low, I don't have to put so much polymer in. So that's something that most people miss, is they, where I'm going to do an oil displacement experiment, I forget about sweep efficiency. I don't care about sweep efficiency. What I want to get is that relative permeability curve, so I can make that judgment about what's the right polymer concentration and viscosity to be injecting.
Thank you.
And then when you get that, it's very important to have the right wettability.
Yeah, exactly. You've got to do the best job you can.
Correct native wettability,
Yeah,
or you get the wrong answer.
You do have to, and you have to use real reservoir cores.
Right.
You have to use real reservoir fluids.
It's not easy.
It's not easy, but it is
Worth.
it is worth it.
Right,
That's the
correct.
key point.
Absolutely.
Yeah, thank you. Yeah. I think we need to make a big focus in our labs on this test now, on real parameters. Maybe we'll invite you to our lab, please.
Okay.
And maybe you can
Where's your
guide us
lab?
in October.
Okay.
Yeah, we'll talk about
Is that a nice place?
I don't know. Yeah, because that's easy there. So, there was a question here or a comment?
Just
Someone else?
one short question
Please,
for the
please.
long-term thermal stability. Do you have some standard time and how long it takes, and do you use the globe box?
The longer the better.
Okay.
For us, it's only 30 days.
Okay.
It can be up to a year. Can
And
be
what's the max time you
like 60 days, thank you, 62 months.
do you use a globe box? Do you use a globe box?
No, we don't have a glove box. If you want to give us a gift, that's fine. Okay, joke. Okay, so guys, actually, I will ask our student. Excuse me. Please, can I ask you a favor? Could you go downstairs and see how we're running on time? Are we good, or we got some more time? I don't understand because we start late. Maybe we have half an hour, so please find it out first. Okay. So we talked a lot about all these tests now. I believe I don't have time to go into details. What I will show you now, well, I will just go very quickly. And please turn off the light. Okay. So we've got here how we do our polymer selection tests. We order lots of polymers from different companies. Here we've got 9 polymer samples. We, as I told you, we do the identification of polymers. We try to describe how it looks, what is the color, what is the main substance content. We measure the viscosity, we measure molecular weights, we measure the density, degree of hydrolysis, insolubles, how much we have there, and then the solution time. In our project, this is the real results from one of the projects. We've got 101 polymer, which was not soluble, bad one. And we get rid of it. So the next one is our rheological studies. just briefly and concisely. So we use our real water and try to see the dependence of concentration, viscosity on concentration. We've got the range from up to 2,000 here. We've got viscosity, different viscosity for different polymers. And then we also do these tests for not only atmospheric temperature, but for reservoir temperature as well. Probably it does make sense to add one or two more graphs here to measure this dependence for two other temperatures. Which ones? Help me out. Which other two temperatures I'm thinking about? We are in Kazakhstan. We've got 4
Winter and
seasons.
summer.
Yeah, thank you. Good, yeah. Randall, thank you. Good one. So yeah, there was a point from Olesya. She said that we've got different temperatures, like different seasons. So in the winter we would have like maybe 10 or in the field, or maybe 0. I don't know. And we may go to up to 40 or 30 degrees in the summer. There is now this temperature, so maybe we should add those to be able to compare future viscosity with the lab tests. And then we've got here, again, the concentrations for different polymers. And now we can see and compare which polymer gives us better results in terms of getting target viscosity, which polymer gives us worse results.
Just one comment, if I
Yeah.
can break in, sorry.
Yeah.
I mean, it may save you some work,
Oh, please.
but there are arguments that, you know, the polymer viscosity will scale exactly with water viscosity, right? So all you need to know is your water viscosity changing with temperature, which you can look up in a book, and you can scale your polymer. You measure it at, say, 25 C, you can calculate all the other viscosities
Nice.
at a whole range of temperatures. You don't have to do all the experiments all over again.
And have like a multiplier?
Yes,
Yeah.
exactly.
Oh, nice.
But that's not fitting her data, right?
Well, I don't know.
Well, look at it, the first one has got the same viscosity at 62 as 25, the next one doesn't, the next one does.
Well, then you have to scratch your head and say, why? I mean, that's really unusual then. Are they,
I don't think it's
are they
unusual.
the same concentrations?
I think this depends on the chemistry of these polymers.
Are they
If they have any
associative or
groups
something? I
that-
mean, I've never seen that before. I don't know if you have, Randy.
Well, my usual assumption is your assumption, but, you know, she's measured it, so.
Yeah. Okay.
Methods is different. Methods are different. Maybe this is the difference. Methods used here in Kazakhstan are different from the, for example, which is used by SPE.
Okay, well, let us proceed. Yes, I'll keep in mind your comments. Thank you. And this questionable moment, yeah. So then we do thermal stability. Here is 28 days, different polymers, different viscosities. You can see this is these are different. Each time, yeah, it represents different point within this period of time. So this is like 0, initial one, and this is the end one. And we can measure how much we lose for each polymer solution. For example, this one, 102, gives us, it's over here. The initial one is 20, and it goes, the end viscosity here is 15.4. The same for the same logic for all these polymer solutions. And now we can analyze and see how much we lose during our thermal stability test. So another one, yeah.
I think it's much better to represent the y-axis as the viscosity loss.
Except the absolute values of viscosity. Okay, yeah, sure. Yeah, we put like this another curve here and see this is the percentage of loss. We just didn't show here. Yeah, thank you. So then we've got our methods for experiment to determine dynamic absorption using real core samples, using different methods. Which methods do we use to determine absorption of the polymer when we talk about dynamic absorption? We've got this Shimadzu equipment, which was suggested to us by you, Dr. Seright, and it's a great one, thank you. We have some missing parts. Now I think we gotta buy it, something to make it work again, but we also, so we've got different values for absorption using hydrocarbon, using nitrogen, viscosity methods, and then we can average them, or we can choose either one, depending on the situation. So we measure this absorption. You see that the values are kind of high. We've got up to 400 micrograms per gram rock here, and we've got around 110 here. So it gives us a variation of how polymer works in terms of its absorption on the rock. And then we do mechanical degradation. The way we do it is we run the polymer solution through our water-saturated core at different velocities. We start with the very low velocity, and then we increase it one by one, trying to represent these processes. So this is our in situ velocity. We've got, maybe we've got fracture velocity, we've got open hole and perforation velocities. So we can also measure the mechanical stability, and you can see for each polymer solution, we've got their losses. Oh, actually, these are stabilities, but we can calculate the losses. 100% minus this value gives us the loss. This way we determine. I understand this is something easy, simple, maybe not so much representative as it could be, but you know, it's better than just using a blender and running through our polymer through the blender, or using the blender. That would be worse. So that's how we do the mechanical degradation, and then we do the sweep efficiency, the one that Dr. Randall just commented on. So we want to know if we have the ability for the polymer to sweep a little more oil once the core gets water flooded. And we do have these small values of increment oil recovery for different polymer solutions. Actually, these values are way too small. We didn't get the reason why this happened, so we just threw out the window this polymer project at the very end and started a new one, because our polymer solution gave more valuable, reasonable increment values, such as 10 up to 15. So those are good, but seeing 2 and 3%, this is, you know, we don't take it.
So the field it was 10, 15?
No, for other lab tests, it's usually from 10 to 15. But here we get only 2-3%, so we don't believe it, we don't trust it. We didn't understand, trying to understand, we didn't give the understanding why it's happening. So we just get rid of this project at all and start a new one. So basically, yeah.
Darya, can we hear from the experts what can be the reasons of that situation? Because we face this sometimes here in Kazakhstan in lab tests when all other parameters are fine and suits the technical data which was provided by producer company, but the oil recovery was such small.
Okay.
Where can be?
So I would look at this 2 ways. I would look at this information and say the primary thing I'm going to try to get from this is relative permeability information. That's the first thing I would do. I don't even worry about that. You want an explanation, and you say, sometimes it does this, it's not very different. Well, you've already swept 14, 13 pore volumes of fluid through, so maybe there's really not that much residual oil left to, or resident mobile oil yet to be moved with the polymer. So that's one possibility. Okay. You think there is a lot left to be moved?
This is one of the tests which was real here, as I understand, and we have a few another tests for this field, and with in frames of another tests, we get results more higher than here.
Okay, so, okay,
And
maybe.
just one question for clarification. What you were saying there's 3% that's a polymer flood following the water flood?
Yeah.
We get that all the time. That's very normal.
It's for us, it's not normal. It's
Because,
very.
and are these horizontal or are these vertical floods?
Those are horizontal floods.
Horizontal
yeah.
floods. I mean, that is normal, what we get.
We-
Because I think I agree with Randy, your water flood has completely gotten all the mobile oil. The only way you're gonna get more oil is go lower interfacial tension. Because you don't really measure sweep. You got a homogeneous core. You're measuring displacement efficiency. The only way you get more oil is to add surfactant. We get that all the time. You do a polymer flood after water flood, you get 2-3%.
And you're saying sometimes you see a big jump, right? That's what
In
you're saying.
lab.
Then you gotta
In
have a
section.
genius core.
Well, so it might be that, and Madar would jump in and say, it depends on the wettability of your core. If your core is really water wet, we would expect this. If it's not water wet, if it's more oil wet, then as Madar would say, you have to look at where you are on your capillary desaturation curve, and maybe that second bump you're getting is due to the wettability that you're actually overcoming the capillary forces enough to do it, so it makes it more complex.
Great,
Right.
yeah.
He's
Yeah,
the expert,
absolutely
so-
agree. So that depends on the variability. Maybe the cores were not prepared properly for these tests. We don't know for how long. Was it enough? Maybe it was not enough because we're always doing in rush.
So do you have the
yeah.
pressure gradient for this one?
Not here, but for sure we do have, yeah.
Yeah,
those
you
files,
can
yeah.
compute the capillary number probably if you are
Yeah.
ahead of the critical
Yeah,
capillary
yeah.
number, then you may have extra recovery, but if you are below that, you may not have much recovery.
Yes, thank you, yeah.
But I would just say again, I would not exclude a project because of that. No way. I mean, because that is, in my opinion, that's
It's okay,
normal.
Yeah, well, for us.
I would not
yeah.
say I don't have a project because of that.
Project is ongoing, but with another polymer which shows in lab like 10, 15, I don't
Yeah.
remember.
Yeah.
Right.
We start,
So
yeah,
same,
for that-
same project, kind of same polymers, different results. In the lab.
All the petrophysical properties are same?
Plus minus.
Okay, yes, thank you. I hear y'all, believe me, I hear y'all and I understand what your message is trying to keep in mind and then hopefully to realize more of what you have said later on. So this is our summary table for this project. We've excluded some of the super bad polymers just because they were either insoluble or it was due to high powder expense or something else. So, and we've got these mechanical degradation, thermal stability values, increment after water flood for the polymer flood, and adsorption values. And we usually compare all these parameters and see which polymer is the best, or which 2 or 3 polymers are the best. This way we recommend them to start the pilot with those polymers and check their quality and their effectiveness at the pilot level. So this is how we do our projects when it comes to polymer selection projects for polymer flood technology. And can someone tell me about the time frame?
Actually, times.
It's out, yeah? Okay, we're running out of time. Okay, so dear participants, dear friends, I wanted to present another topic here, but I don't have time. But I'll just tell you what I wanted to talk about. I wanted to tell you about the results of another lab test on the chemical compositions for conformance control treatments and how we do it. I won't, since we're running out of time, I will just give you one, no, I'm sorry, I gotta go here. I'll just show you the very last table. It's a summary table showing that we do pretty much the same experiments. We do the physical and chemical check, and we do this rheology test here. We see when gelation starts. We see what is the pressure gradient, initial one, what is a resistance factor for this conformance gel, conformance control treatment gels, what are the RFs, what is the pressure gradient during injection, which pressure we get, maximum pressure we get when we inject. We know that the pressure will build up up to which point, and for sure we measure the water isolation level, which is what is the ratio of initial permeability up in comparison with the final permeability after you form your gel. So this way we do our composition, chemical composition selection for conformance control projects. And we've got lots of questions to our dear experts, to Dr. Randy, to Ludwig, and we already got a lot of answers. Thank you for the answers, for helping us with understanding some of the processes. What I suggest to do, now we have to finish. We've already discussed a lot of things. I made lots of notes here for myself, for us, and we've got two more presentations. One I just presented, I finished with my presentation, but there are two more. One presentation gives you the answers for these questions, and these answers are given by Dr. Randy and Ludwig. If you want to have this presentation with a question and answer, I will be very glad to send it to you. So if you want, please come to me and leave your email address with your name. I will send it to you. It will be like a small guidance for you to get the answers for these questions. And these are not the whole list of questions. There are much more. This is first my message. The second message of mine is the following. We've got another presentation, the third one, which is done by Ludwig. But we don't have now time for Ludwig to present his presentation. Ludwig, do you agree for me to send your presentation to others as well?
Yes.
Yeah, thank you. So this presentation could you briefly tell us the content of what it's about?
Yeah, the content is to actually how to avoid misunderstanding in a multicultural way of working. We are coming from different places, speaking different language. But we are, all of us are scientists, or at least I want to believe I am one scientist, and even though we don't speak the same mother language, I'd like to, all of us speak the same technical language. And when we speak about molecular weights, intrinsic viscosity, there's multiple ways to even understand, but especially to measure this parameter, which ultimately doesn't mean anything, because as we don't measure the same way, we cannot compare
the results
as they are not performed the same way. So I just wanted to focus on you are conducting a lot of experiments, and you say also you are rushing against time. I would like to also have a final guidance is to is to remain as simple as possible in the evaluation, in the way of doing. I mean, and remaining practical. Basically, I'm doing similar work as work for industrial company, not for oil producer company, but we do rheological evaluation, thermal stability, mechanical degradation, core flow. Core flow we don't do all the sets of evaluation 100% of the cases. For example, thermal stability, I can back up on probably 10 to 15 years of experience, and I have a pretty good assurance of this polymer will be stable in such condition. I can redo for the partner to reassure him the result, but I'm already pretty sure about the selection. Viscosity curve is with a rheometer, Anton Park, Nexus, or viscometer, or Brookfield. Brookfield is my friend. LVT Brookfield is my friend.
Yeah.
With a UL spindle is very, very, very simple. I know that a lot of capillary test viscometer are used. I use that from the past, but the results from them can vary. I mean, I observe that it is people doing experiments may vary the result. It is person dependent. So as it is human dependent, I always look at the data very skeptical. But what I want to say is really to have practical, simple evaluation that ultimately will be useful for the implementation of the project and for also the reservoir simulation, which is the entry point of building the case.
Yeah, thank you. So yes, there is another gift for y'all if you want to give it, or if you want to have it, if you want to have this gift. It's Ludwig's presentation. So 2 gifts for you if you want. The first one is Dr. Randy's presentation with the question and answers, and the other gift for you is the Ludwig's presentation. So I sincerely, from all my heart, thank you all for questions, comments, for being here today with us. I hope you enjoy staying in Almaty in this great time, in this great season outside, good weather. Sun is shining, so everything is very nice. So if you have any questions, comments, if you want to leave your email, please go to this table. We will also have to sign the protocol, but I don't want to force you to stay here for signing. I will just ask my dear subject matter experts, you, Dr. Randy, you, Ludwig, please sign it, at least y'all and Yerbolat, you. So this will be enough, and we will try to finish up shortly with the protocol. So thank y'all.
Thank you.